Hi there, welcome to this Maths for Engineering 1 Outcome 3 lecture on complex numbers. So this lecture is going to be on an introduction to complex numbers. We're going to look at Argand diagrams and we're going to look at some basic algebra of complex numbers. So a complex number, sometimes called an imaginary number, arises naturally in mathematics. It is an attempt to give a solution to a problem where no real solution exists. So physically, complex numbers don't really exist, but in theory, they exist. They do appear in some forms of engineering as well, such, for example, three-phase electric circuits. So a complex number comes from attempting to do the square root of -1. If you try and do this on your calculator, it will come up with an error. In fact, if you take the square root of any negative number, it will always give you an error. In this unit, what we will do is we will represent the square root of -1 with j. So j is equal to -1. If you have done higher before, you may have seen it written as an I instead of a j, the I being an imaginary number. But because we're working in an engineering context, we use j to avoid confusion with current, which is usually represented by I. So the convention at the moment we will be using will be j. So let's see where a complex number comes from. So if we take this example, solve the quadratic equation, x squared plus 2x plus 5 equals 0. Now, you should be able to solve that quadratic equation using the formula x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. You should recall that quadratic formula. That is when we have equations of the form ax squared plus bx plus c is equal to 0. So if we sub those numbers into the equation to solve for x, a being 1, b being 2, and c being 5, so we get minus 2 plus or minus square root of b squared, so 2 squared, minus 4 times a, which is 1, times c, which is 5, square root of all that, and then all divided by 2 times a, so 2 times 1. If we then start to simplify this, what we get under the square root is 2 squared is 4, and then 4 times 1 times 5 is 20, so 4 minus 20 is negative 16. Now, therein lies the problem, because we can't take the square root of a negative number, as I illustrated in the previous slide. What we can do, though, is we can use this idea that j is equal to the square root of minus 1. So, what we can say instead is, instead of square root of minus 16, we could call that square root of 16 times by the square root of minus 1. That is the same thing. Now, we can do the square root of 16. We know what that is. And we know what the square root of minus 1 is because we've illustrated what it is here. So what we can get is the square root of 16 is 4. And the square root of minus 1 is j. So we have some sort of answer. Now we just need to simplify that. Okay, now both of these numbers here can be divided by the 2. So we are left with 2 divided by 2 is 1, so negative 1, plus or minus, and then 4 divided by the 2 is 2j. So we've got an answer. It doesn't exist in reality, but it exists in theory as a solution to the equation up here. Now it says express your roots in the form a plus jb, a plus or minus jb, sorry, which is kind of what we've got. But the convention when we're writing a complex number is to write the j in front of, in this case, the 2. What that does is it just shows us that it's different from an algebraic expression and is instead a complex number. Okay, so that's the only time that you will see a letter in front of a number conventionally in mathematics. In addition to this, we need to be able to label a couple of these parts for the next part of the task. So this part here, without the complex number, the -1, this is called the real part. Whereas this bit here, the 2, this is called the imaginary part. Okay, and that's going to help us for the next couple of slides. So just moving on to the next part. What we're going to be looking at now is an Argand diagram. So complex number may be represented by a diagram on a rectangular set of axes called an Argand diagram. On an Argand diagram, the horizontal axis is used to represent the real axis, that is the real part of the complex number, and the vertical axis is used to represent the imaginary part of the number, the imaginary axis. And then a straight line is from the origin to the point is plotted using the real and imaginary part of a complex number to represent this complex number. So let's look at that in practice. So show the following numbers on the Argand diagram. You can see here that we've labelled this horizontal axis as the real part, and then we've labelled this vertical axis as an imaginary part, or J. Okay, so the real part, let's look at this first complex number here, Z1. The real part is 3, and the imaginary part is 2. So when we come to plot that, we're going to go 3 across and 2 up. And we label it with an X, join it up from the center, and it's called Z1, so we label it Z1. Like so. So that is how we plot Z1 on an Argand diagram. Z2, the real part is -2, and the imaginary part is 4. So when we come to plot it, we're going to go -2 across, and then 4 up. Mark it with a cross, label it Z2, and join it to the center. Just going to rub out these guidelines so we don't get too messy. Z2. Okay. Z3, the real part is -3, and the imaginary part is -4. So when we come to label that, we're going to go -3 across and -4 down. Put across, label it Z3, and then join it up to the center. So that's important. You can't just label the cross and label it Z3. It does need to be joined up to the center. That's how an Argand diagram is constructed properly. And finally, Z4, the real part is 1. The imaginary part is -3. So we go 1 across and 3 down. And that is going to be Z4. And don't forget to join it up to the center like so. Okay, so that's how an Argand diagram is constructed. They're useful things to be able to use, as you'll see in lectures up and coming. So we're going to look at some algebra of complex numbers now. So when we add or subtract complex numbers, what happens here is the real parts added together or subtracted, depending on what you're doing, and the imaginary parts are added and subtracted. It's just like normal algebra, really. You treat the real parts together, you treat the imaginary parts together, and you collect the like terms. Okay, so if we take this first example here, example 1, Z1 is 5 plus J6, and Z2 is 3 plus J4. So if we add together Z1 plus Z2, that is going to be 5 plus J6 plus 3 plus J4. Now, the real parts go together, and the imaginary parts go together. So we get 5 plus 3 for the real part, which is 8, and J6 plus J4 is going to be J10 for the imaginary part. So it just behaves like a normal algebraic equation in that sense. Real parts, imaginary parts, collect them. So example 2, Z1 is 5 plus J6, Z2 is 3 minus J4, so simplify Z1 minus Z2. The thing to be careful of with these sort of questions is your negative numbers. That's always what throws people. So if we've got 5 plus J6, we're going to subtract all of 3 minus J4. Now, just be careful because it's subtracting the whole thing there. So we are going to have a double negative when it comes to the imaginary part. So what I'm actually going to do is I'm going to simplify that bracket. We've got minus of 3, so that's going to be minus 3. And then we've got minus of negative J4. So that's actually going to be plus J4. So just be careful when you've got two negatives. If you need to revise your negative numbers, you need to go back and do that in your own time. So once we've done that little bit, the real numbers go together, and then the imaginary numbers go together. So 5 minus 3 is 2 for the real part, and for the imaginary part, we've got plus J6 plus J4, so that's plus J10. Okay, and moving on to the next slide now. What we can also do is multiply by what we call a scalar. So a scalar quantity is just another number that we multiply by. So what happens is the scalar, whatever it is, multiplies the real and the imaginary parts. So in this example here, if Z1 is 2 plus J5, find 3Z1. What that means is we're just doing 3 lots of 2 plus J5. So the 3 times is both the 2 and the 5. So we get 3 times 2 is 6, and 3 times 5 is 15, so J15. Okay, just behaves like a normal algebraic equation. And if we just do a few final examples here. So we've got Z1 is 3 plus J5, Z2 is 2 minus J10, and Z3 is minus 0.5 plus J1.5. Sorry about that. Yeah. So firstly, we've got 2Z1 plus 4Z2, so work that out. So we've got 2 lots of Z1, so 2 lots of 3 plus J5, plus 4 lots of Z2, so 4 lots of 2 minus J10. So we need to multiply those scalars out first, and then we need to collect the like terms. So we're going to do the 2 times the 3 and the 2 times the 5. And we're going to do 4 times the 2 and 4 times the minus 10. So 2 3s are 6, 2 5s are 10, and then 4 2s are 8, and 4 times minus 10 is minus 40. And then remember to collect the like terms. So that's the real parts, that's the imaginary parts. So 6 plus 8 is 14, and then plus J10 minus J40 leaves me a total of minus J30. That's your real part, that's your imaginary part. Okay. Example B. 3z2 minus 2z3. So we've got 3 lots of 2 minus J10 minus 2 lots of minus 0.5 plus J 1.5. So multiply these out again. So 3 times 2 is 6. 3 times minus 10 is minus 30. And then we've got minus 2 times minus 0.5. 2 minuses making a plus 1. And then minus 2 times J 1.5. So that is minus J3. Again, just be careful with your positives and your negatives. And then we need to collect the like terms. So that's the real parts, that's the imaginary parts. So 6 plus 1 is 7 for the real part, and then minus J30 minus J3 gives me minus J33. So that's the real, and that's the imaginary. Okay. And then final example for today. And we're going to do 8z3 minus 2z1, so that's 8 lots of minus 0.5 plus J1.5 minus 2 lots of Z1, which is 3 plus J5. So 8 times minus 0.5 plus J 1.5 minus 2 lots of 3 plus J5. Okay. Multiply these out. So 8 times minus 0.5 is minus 4. 8 times 1.5 is 12. Minus 2 times 3 is minus 6. And minus 2 times 5 is minus 10. So the real parts, we've got minus 4 and minus 6. And the imaginary parts, we've got J12 minus J10. So looking at the real parts, we've got minus 4, minus 6, giving me a total real part of minus 10. And the imaginary parts, I've got a total of plus J12 minus J10, so that is plus J2. That is your real part. That is your imaginary part there. Okay. So that concludes the lecture for today. I'll now move on to showing you where you need to be on Moodle. So if you go onto Moodle here, click on your Engineering Maths 1 course. And then we're doing outcome 3, if you recall from the introductory lecture. Okay. Now, when you get down to outcome 3, if you click on outcome 3 notes, we'll open a PDF. Okay. Now, the notes are the ones I've just been doing. So you then need to go and find worksheet 8. Okay, it's towards doing the second half of the outcome here, and this is on page 72. So worksheet 8 on page 72. Okay, It's got question 1, show these on an Argand diagram, and then questions 2 and 3 are doing algebraic simplification of complex numbers. Now, the good thing about these workbooks is that there are answers at the end. Okay, so you can find the answers at the rear of the book. Okay, so if you've got any questions, please send me an email, or you can wait until next week's Teams catch-up meeting. Okay, thanks now, goodbye.